Okay, so for 13.2, we're going to talk about thermal expansion and what happens in a solid and a liquid. So when you look at this image here, these joints are designed in such a way that they allow for stuff to expand. So we have a picture here of a bridge in New Zealand, and basically the concrete expands as it heats up. And so this is a kind of a neat design that if that concrete, because due to the heat it expands, what happens is the concrete will push this way, and let me just draw a little picture. If for whatever reason the concrete expands, it might force this part of the bridge this way and this way, and there's enough of a gap in here that allows for expansion, and they'll overlap, and so that's good because we don't if they didn't have that device in there to deal with the expansion, then the bridge would buckle and you'd get a big, huge bump in the middle of the bridge, and it would actually cause a lot of damage to the bridge. And so, in general, objects have a tendency to expand in all directions as the temperature increases. And a lot of this has to do with kinetic energy. In these images, these drawings, the original boundaries of the objects are shown with solid lines, and then the expanded lines are the dashed lines, and the area increases in both length and width, and the area of the circular plug increases. So if the plug is removed, the hole it leaves becomes larger with an increasing volume, so that actually can change. And if the plug is removed, the hole is larger. And just as if the expanding plug were still in place, volume increases because of 3 dimensions increase. And so basically what's going on, what pushes this out this way is the molecules, as they heat up, they get more energy and they kind of bounce back and forth like this, and then they push against each other, and that causes this to expand out. So this will expand out, and this expands out just a little bit when it heats up, depending on the material. And so that depends on the molecular bonds inside of the material and how much room those molecules have to kind of bounce off of each other. And so here I have a chart that has the density of water as a function of temperature. Note that the thermal expansion is actually very small, but the maximum density is plus or minus 4 degrees Celsius, which is just a little bit more than the density at 2 degrees. Sorry, I yawned for a little bit. And so there isn't that much of a decrease in the density of water. But you could see that there's a maximization, right? Like there's a sweet spot right here for water. And remember that this is when water freezes at 0 degrees. So that's when it freezes. I'm going to try to spell freeze. So there's this sweet spot as the water starts to melt, it expands a little bit, and then it'll go back down. So not everything is going to constantly expand as you increase the temperature. Sometimes it's not linear. I misspelled the word freeze. Okay. Sometimes it's not linear. There's different things. It depends on the molecules themselves and what holds the molecules together. And so there's sometimes the phase change is actually the breaking of those bonds. And that breaking of the bond is just, it has so much kinetic energy, it just breaks away. Because the gas expands more than the gas tank with an increase in temperature, you can't drive as many miles on empty in the summer as you can in the winter. In other words, if you drive with this a little bit past the E mark in the winter, well, that's fine because the gas is kind of shrunk in like this, right? If you wanted to think of it. And as that temperature increases, the gas expands. And so if we were to measure the volume, based on the actual liquid gas. The gas is expanded in the summertime, so there's not as much gas in the tank, or the tank expands. So that's another thing you can think about too. The tank might expand, you know. So anyways, that may not be the same in the winter as it is in the summer. It really depends. So this is what happens when the concrete like stretches. So sometimes it'll push the concrete together. So when it's hot outside, this expands, right? And it pushes this way. But then when it's cold outside, it shrinks back. And so when it shrinks back, sometimes it leaves a little bit of a gap. And if there's a gap, like these cracks right here, and it rains outside, right? And that water penetrates down underneath the asphalt, and cars put pressure on it and stuff. Sometimes it could push the dirt out of the way. Sometimes the water fills in there. And that's what causes potholes, believe it or not. Now, for the homework, what I really want you guys to do, we'll do this one last thing. So when we talk about expansion of a solid or a liquid, depending on the application, sometimes we just talk about the cross-sectional area. And you can read the textbook for more information on this. But we have a tendency to focus on the cross-sectional area, especially when it comes to like fluid dynamics, because the length or depth, this part right here, if it's some sort of flow, it's factored into the equation. So a lot of times we'll just look at some sort of cross-sectional area. In other words, we don't always use the volume of something. We just look at the expansion of the cross-sectional area. And if we could do the math on the cross-sectional area, it has an impact on the volume, right? So that's what I mean by when I say it's factored into the equations. And so the last thing that I want you guys to do is there are some example problems in the textbook. And so I just want you to go through and write those down in your notes. I'm not going to write these in the notes because my tablet is not working today. But just write down, there's like 3 or 4 example problems in your textbook from 13.2. So just read them and write those down. And that's it. Actually, I could probably pull them up. So when I say examples, what I'd like for you guys to write down in your notes are these examples. So, for example, this is the formula for thermal expansion. You need to write this down. It's going to be that the volume is equal to 3 times alpha times, or the change in volume is equal to 3 times alpha of the initial volume times the change in temperature. And then that could also be the same as the change in volume is equal to beta times the initial volume times the change in temperature, where B is the coefficient of the volume expansion and beta is equal to 3 times alpha. And then there's this other formula too. You need to write down the cross-sectional area. The area is equal to 2 times alpha times, this is the final cross-sectional area, is equal to 2 times alpha times the initial area times the change in temperature. And so remember, if something gets colder, that's a negative temperature change, okay? And alpha is the coefficient of linear expansion. And so for 2 dimensions, we have 2 times alpha. For 3 dimensions, we have 3 times alpha. Those are the formulas, just jot those down. And then if you're wondering what alpha is, somewhere in here I saw the, here are the, here's the alpha, the coefficient of linear expansion. For aluminum it'd be this number, for brass it'd be this number. So you'll need to jot these down too, so that way you'll have them with you when you go to use your notebook. And then this would just be beta, which is just 3 times this number, okay? So jot those down. Here are some more examples. You can, so in linear dimensions, this will be the change in length is equal to alpha times the initial length times the change in temperature. So that's the linear. This is the area formula. Write those down. This is the volume formula, which is 3 dimensions. And then there's this one here where you're calculating the actual gas versus the gas tank. So what you would do is you would calculate the volume in a steel tank and then do the expansion of the steel tank based on the numbers in the table. And then you would do gas or gasoline. And then the difference in volume is gas minus the volume of the steel tank. And then you just go through and figure out what the difference is, okay? And then lastly, we'll talk about thermal stress due to gas pressure. And so just jot all this stuff down. We'll talk about, remember that pressure is equal to the force over the cross-sectional area, and then based on this formula, we can replace that with the change in volume over the initial volume times B. Remember that that's the bulk modulus for gasoline. So bulk modulus, you can click on this, that's stress and strain. That'll take you to a table on bulk modulus numbers for various materials. That's the one for gasoline, okay? And then they give you an example problem that you can kind of crank through and then find the answer. And so that's it. That's all you got to do for your notes. And then this one, you're going to calculate some expansions and stuff, and then when you're done, you can look and see how you did. Like what happens if you go from block A to block B? How does that work? So I'll let you read and write that down, but that's for your notes, and that's it.